Hello and welcome back to Calculus 1 section 5.1 on approximating area under the curve. So chapter 5 is all about integration, all about figuring out area under the curve and also what integration means. We already did basic integrals. Now 5.1 will not have any calculus in it. So I hope you're not going to be disappointed. We are literally going down to the middle school level math where we are looking for area of a rectangle, right? So we would like to find a way to approximate area under the curve because not every shape is easy to calculate area. For instance, if you have a regular triangle, this is in my case, it's all crooked, hold on. And this is the height, this is the base. Area is 1/2 base times the height you move along. You have a circle with the radius r, area is pi r squared. You have a rectangle of some kind with a and b, area is a times b. Even if you have the trapezoid and all other shapes, right? You have some height over here, you have your A and your B. Area is A plus B divided by 2 times the height. So there are a lot of these shapes, right, that we just know the area formed in geometry, and it's easy for us to implement that even if we have a graph. So if I want to, let's say, calculate area under y equal, let's say, 2x from x equals 0 to x equals, let's say, 4. Or let's not do 4, it's too far out. Let's do 2 because of the graph is small. All I need to do is to graph this function and then go to the interval 0 to 2. And I actually don't need calculus or anything else. It's just simple. Right, so 2 units up, 1 unit over, 2 units up, 1 unit over, 2 units up, 1 unit over. It goes like that forever. Now 1, 2. There you go. So now you see that this length over here is 2, this length over here is 4, and you just unleash the triangle formula and you get 4 units squared. Now you can actually see that, right? If you zoom into this and you say, oh, okay, so the way this line goes through, you see that you can take this part and fit that part in here. Sorry, lies. I'll try to do a little bit better job over here, but I want to show actually physical 4 squares, right? So we already see 2 squares, right? And now all I need to do is to fit this portion here, and that will create another square, and then take, let's say, this portion and fit that here, which would create another, and there's your four full squares, right? So it is very easy for us to verify this calculation because we do see 4 squares in this calculation. Same happens if you are trying to find area under, let's say, constant. So if you have something like this and you put this constant line here, which is y equals 3 in my case, and let's say, so y equals 3 on interval 2 to 6. Okay, 2 is right here, 3, 4, 5, 6 is right here, and I'm looking for area under the curve, and the curve is just a straight line. Earlier the curve was also a straight line, but there it is. And then I can now say, oh, that's 4 units, that's 3 units, so area is equal to 4 times 3 equals to 12. And you actually do have 12 of these rectangles. If you zoom in, and you will find 12. So units squared, whatever the units are. Now, if you have, let's say, yeah, tablet moves. There we go. So you have a quarter of a circle, and the lengths over here are, let's say, 3 and 3. Well, the area in this case would be 1/4 of pi 3 squared, which would be 9 pi over 4 units. There we go. Units squared. What is this R doing here? Get lost. So all of these shapes, right? And we can find the area. Now, hell breaks loose quickly because my function could be, let's say, square root of x, right? And in that case, good luck. So what is the area from, let's say, 0 to 4? Like, what's the area there? You say, well, that's going to be easy because I can just go 1, 2, 3, 4, and the area is all of this. Yeah, but how do you compute it? Because it's not a triangle, right? There's this belly that it's sticking out. It's not a rectangle, right? Because now that's all error. So it's curved, right? And it's not a circle, so can't use that equation either. So how do we figure out the area under? Now someone might say, well, yeah, why would you care for the area anyway? Well, that could be energy curve, and right, the area under the curve becomes energy. So, and that's very important. How much energy do you get to store in a battery in terms of chemical energy, right? It depends on, determines also how much charge you get to have, right? And how long the battery can last working in whatever. So the batteries are rated not just by their size and voltage, but they're also rated by how many milliamp hours they can produce. So that's all, you know, dealing with chemical engineering and materials and all of that kind of stuff. So you have the better batteries and not so good batteries, right? Depends on what you buy. So how do we find now area under this? And the answer to that obviously later on will be, well, we are going to use calculus and integrals and so on, but we need to build to that point. And what we are going to do here is we are going to divide this into these regions. Now, you don't have to divide on integers. You can divide any way you want. But the interesting thing is what you created here is you created a framework for you to create rectangles and approximate area under the curve. So if you take a look at, let's say, this one here from 3 to 4, if we take this one as a guinea pig, all right, and you look at this one, you will notice that on the top of this, it's not yet rectangle, right? Because you have these 3 straight edges, right? And the top one is curved. So that's the bad one, right? So you have a choice of making an approximation by striking the line this way, or you can go to the right corner and strike your line that way. In either case, you are getting error. but at least you are computing a rectangle. So it's like a trade-off. Oh, I can calculate. I know it's not exact, but at least I can calculate. And you can do that on every single one down the line. So if I go to the previous one, I can go to the left corner, and then the previous one go to the left corner, and then this one, wow, look at the red one. It completely killed the area on the first rectangle. Like the first rectangle has 0 area because the height is 0. But that's okay. Let's take a look at blues, right? The blue one is going to emerge and go this and go like that and go like this and go, wow, the blue one is really overshooting. Well, pick one, right? Don't be negative all the time. Both of them are approximations. Both of them are going to be wrong. Now, both of them are going to be wrong approximately the same amount. So pick one and solve it. So we're going to pick red ones, and then we're going to do a separate problem, same problem for blue ones. So now I'm taking the blue ones off, because what I have here with the red ones is what we called left-hand approach. So left-hand approximation. I said approach, but that's the wrong word. Left-hand approximation. Why is it called the left-hand approximation? Because each rectangle that you are looking at, and you have 4 of them, is using the left side to draw the rectangle. Because when I draw the shape like this, I have the left side and the right side. So the left side is the one where I draw the rectangle, which means I have error above. If I go and I draw the rectangle from the other side, like that, then I did it from the right side, which is why it's called the right approximation. So that's something that, it's a very easy concept. I mean, it's left and right. It's just, I want you to know exactly why it's called left-hand approximation. So each one of these 4 rectangles is going to compute values starting from the left corner going over. Now, what do I have? Well, for the area, which will be approximated by, that's a squiggly equal sign, AL, meaning area with the left-hand approximation, we're going to have a function computed at 0, because that's the height, times the width of the rectangle is 1. Plus, for the second rectangle, which is this one, we are computing the function at 1, and we are also multiplying it by 1, which is the width. For the third rectangle, we're computing function at 2 times 1, which is the width of that rectangle. And finally, the one that is shaded blue is computing the function for the height at 3, and we are multiplying by 1. So this point here, right, the left point on which I used to create this rectangle is 3, f of 3. That's what the point is. So you see that the height is the value of the function, and the width is 4 minus 3, which is 1. So now this is square root of 0 plus square root of 1 plus square root of 2 plus square root of 3, which is 0 plus 1 plus 1.4 about, right, plus 1.7 about, and all of that stuff is 4.1. So we approximated that area is 4.1. It's not, right? We know that the actual area is more than that. We know that area is bigger than 4.1 because look, all of these places here, they're all error, and they are not the part of 4.1. So 4.1 is a low. We have a lot of error there. Now we're going to rinse and repeat, except we're going to use the right-hand approximation, the right side, to draw these values. The angle at which my tablet is on the desk is very difficult to draw straight lines. So here's my square root of x again, and now I'm going to divide again the same divisions, 1, 2, 3, 4. But this time around, I'm going to go to the right point and create my rectangles. Cool. Area is approximated by right-hand approximation. And now look what I have for the first rectangle. I'm using right side to compute. So it's f of 1, because that's the height. F of 1 is the height, times 1, which is the width. Move to the next one. F of 2 times 1. Move to the next one. F of 3 times 1. And the last one is f of 4 times 1. If you take a look at that last rectangle, you see that the height of the rectangle is this value, which is actually y computed at 4. So this mess is square root of 1 times 1 plus square root of 2 plus square root of 3 plus square root of 4, which is 1 plus 1.4 plus 1.7 plus 2. Right? And all of that equals to 2, 3, 4, 5, 6, 1. 2, 3, 4, 5, 6, 1. Yeah. So we say that the area is approximately 6.1. We know it's not. It's approximately 6.1. And we also know that the true area is actually smaller than 6.1. Because look, you calculated into your area all of this that it's actually not part of your area. So the number you are getting is actually bigger than the number that you're looking for, because it has error in it, right? All of these values there. Now, between the area to the left and area to the right, you can say, well, at least I know that my true area is between 4.1 and 6.1. I don't know what that area is yet, but, you know, I know that area is in between these two numbers. And I know it can't be equal to any of those two numbers because the way we set up the problem, we can see the error, so we know, right, that this can be equal. And believe it or not, that's it. Now we're going to put this into nicer mathematical wrapper, but if you know the formula for area of the rectangle, you just need to write it out, and you're done. Like that's it. There's no any advanced mathematical procedure or calculus or anything in this particular case. It's just, this is it. Literally middle school, right? Calculations. So now let's take a look at a general case where you have a function f of x, there we go, and you come up with a rectangle here. Now see, when you make this rectangle, we can use the left side. You will always be computing your function value at the point where you created your rectangle. Now, this is going to be some xn, and this is going to be xn plus 1. Now, what do I mean by that? Well, when I partition my function like this is my x0, x1, x2, x3, x4, xn. The next one is xn plus 1. The next one is xn plus 2. right? So it's just an index to show us, right, this where they and how they connect. So when we look at this, we see that this will also be on some interval that is like the interval at which we are looking, right? And then we have one of these representative rectangles inside. Now, this value inside, the width, is delta x. And the reason why we call it delta x is obviously it's a difference of two x values. So it's very simple to understand, right, that delta x is b minus a divided by the number of rectangles. Because if you have your a and b like this, and then you do divisions inside, you say, oh, I have 1, 2, 3, 4 divisions. So each one of these delta x's is supposed to be the same width. It doesn't have to be, but it's for simplicity, right, of calculations, we always make it to be the same. So you say, oh, delta x is, you take b all the way out minus a all the way out the other way, and divide that by how many delta x's you have, and you have 4 of them, right? Because you can think of it this way as well. You can say, oh, these 4 delta x's are equal to b minus a. And then you just divide both sides by 4. But technically, you know, this is your formula for delta x. So now I can say use 3 rectangles, use 6 rectangles, use 17 rectangles, in which case your n becomes n is number of rectangles and ab is the interval. So ab is the interval and n is the number of rectangles. There we go. So now I see that I can partition my problem as many times as I want, and there is actually a benefit and a drawback to it, like everything else in life, right? Things are always in balance, if we learn anything from Star Wars. So we look at the problem, and if the number of rectangles is not commanded, right, to be 4 or 6 or whatever, or 5, you pick a number of rectangles. Now, the interesting thing is that, and you can clearly see that, right, when we draw now next picture, the more rectangles you have, less error, better the precision, right? Less error you have. But then you have more rectangles, which means more calculations, which obviously if you are a student at Rutgers and NGIT, you would worry about it because they don't even give you the basic calculator to compute these things on the exam. So yes, you have to take all of the values, right, to know all of the values and so on. Now we do have a basic calculator, so we can divide by whatever. So what do we have here? Here is another picture. So we're going to go back actually to our square root problem. So it stays the same. We should curve a little bit more, but it's okay. And I'm going to put my 4 divisions just like I had them earlier. Now I can use my formula, which I can use my, I'm just going to see, my UPS is complaining. I just want to see what it is. There was a voltage drop in a neighborhood. It's okay. So, I mean, if I lose electricity, we're still on because I'm operating on the batteries here, so it's fine. If you went, yes, you might lose power, there's still going to be a class. So yes. Anyway, so we have this situation from before, and let's take our our left approach. There we go. And my delta x was 4 minus 0 divided by 4 rectangles equals to 1. And we had, right, each one of these. You can actually see from 0 to 1 is 1 unit, from 1 to 2 is 1 unit, 2 to 3 is 1 unit, right? So you see the width of each rectangle is 1. And then we calculated those heights. Now we did approximate the area to be, from the left, 4.1. And we knew that that area was less than actual area. So actual area is more than 4.1 because there is a lot of error. But now, when I go purple over here and say, I'm going to partition this more. So let me double number of rectangles. And now, draw rectangles from the left. I hope you see that we eliminated this error, this one, and this one. These errors have been eliminated from the calculation. And the only error that remains, right, is all of this, all of this, all of this. Right, so there's still error, but less than what it used to be. So these these blue X's is eliminated error. And I eliminated that error just because I went from 4 to 8 rectangles. I could have done it with 5, could have done it with 10, right? As long as you have more rectangles, right, than the previous calculation, you will have better precision. But did I gain? Actually, well, that depends on your calculations. And, right, obviously you never gain when you do this by hand, but those of you that, right, think that are computer science, right, you're not going to be computer science until you program this, right, in Java or Python as soon as you can. Because why would you ever compute this by hand? Look at this now. A is approximated by AL. Oh, first I need to calculate my, and I'm going to do this purple. So my delta x is 4 minus 0 divided by 8 rectangles. So my delta x now is a half. And my calculation is going to be approximated area on the left. And that is f of 0 times 1/2. That's the first rectangle that has nothing to bring to the table. Plus, and now the next rectangle is f at half, because that's the next number where the, right now you have it half and 3 halves and 5 halves and 7 halves. Right? They are all now rectangles. So f of 0 is the first one, then the half is the next one, times 1/2 delta x, plus the height of the next one is 1, so f of 1 times a half, plus f of 3 halves, that's 1.5, times 1/2, plus f of 2 times 1/2, plus f of 5 halves times 1/2, plus f of 3 times 1/2, plus, kill me now, f of 7 halves times 1/2. And then we're done. You do not use 4 because there is no rectangle to the right of 4. So every number that you are using in the left calculation has a rectangle to its right. That should make sense, right? If you're using the left point, the rectangle is to the right of that point. So there is no rectangle to the right of 4, which is why we are not using plus f of 4. And also, you already have 8, if you think about it. 1, 2, 3, 4, 5, 6, 7, 8. There they are, right? So 8 rectangles, 8 calculations. There's no reason to bring in the 9th if you have 8 rectangles. So you will always exclude last point for left, and you will always exclude first point when you're doing the right. Anyway, all of this mess amounts to, you can factor 1/2 in front, and then just have your square root of 0 plus square root of 1/2 plus square root of 1 plus square root of 3/2 plus square root of 2 plus square root of 5/2 plus square root of 3 plus square root of 7/2, and then you go and you do your calculation. So you see that we made calculation worse, because we have now to worry about square roots of these fractions and all of this kind of stuff, right? We didn't have to do any of that before, but this answer is going to be better. And the idea is, right, the more rectangles you have, the better the precision. Which is why I'm saying, like, even if you're not computer science, go program this, right? Because programming skills are important in every aspect of your employment later on, right? No matter which kind of engineer you are, right? You will have to, I mean, you can be in business, you can be, it doesn't really matter, right? Coding is something that should be today almost as important as writing. So write a code. It's a simple loop to compute these things. You can hard code functions into the software, which means that you can ask for input, like the interval, let's say, and the number of rectangles, right? And then compute your delta x, and then use that to compute the rest. Now, over the years, because I always give this as, you know, an unofficial homework assignment, which is just like life skills for later. Students do this to various degrees of success, right? Depends also on how interested you are in these kind of things. So some students would write a code that just spits out a number and you're done. But then some students say, okay, pick which method, left or right, and then pick everything, right? Some students did even scanners for functions, which is actually a complicated thing to do. So, I mean, not complicated, but if you don't have programming background, it becomes complicated. So, you know, for everyone, with or without programming background, you should all be able, the entire class should be able to code, let's say, left-hand approximation with the input of number of rectangles and the interval. It's a simple loop, like 10-15 lines of code at most, and that's it. You can solve your problems with it, right? But the most important aspect of that is to see what happens when you put 10,000 rectangles, and then you put 12,000 rectangles, and then 15,000 rectangles, and you realize that the result is always the same. Because you used so many rectangles that the error is so minuscule that it's not going to be detected for, we don't even know how many, well, we can figure out how many decimals down the line. So you might have your first 12 decimals match, right? Once they start matching at some point, they're just going to keep matching throughout, no matter what amount of rectangles you put. So it's a lot of cool things that you can do with this, right? And it's a good learning experience for you, especially if you never coded before. Now, is there a way to compress all of this? And the answer is yes. So that representative rectangle that we had, there was xn and xn plus 1 between a and b interval. We said delta x is b minus a divided by 2. Oh, sorry, by n. By n, number of rectangles. And now your area is going to be approximated by area from the left. Now each one will have delta x. So kick delta x outside, and inside the bracket you have f or a. Now that a is also known as x0. Plus, and now you move 1 over, that's x1. Plus, move 1 over, x2. Plus, f of x3. Plus, dot, 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 f of x n minus 1. Remember, you're not using the last point xn or b for the end of the interval, because the last one does not have, right, if it's a left approximation, the last point does not have a rectangle on its right. So we can't do the last one. And then area can be approximated by the right hand, which is again the same thing, but now you're not starting at x0, you're starting at x1 for the same reasons like before. And we'll just go through all of these again. And now you are using the last value, which is technically your b. What you see here is the entire method. Now I know it looks bad, but you're just computing function values and then you're adding those numbers. We haven't done any calculus, right? That's why I said middle school level. Pick out the value, compute the function, and then bring it back into the formula. Now, there is one more way in which we can compress this, and we have to learn summation notation for it, which we will. But before we get there, let's see. I'm going to give you a few moments to work on approximating, let's say, 3 over x on 4 to 7. Use 4 rectangles. I purposely didn't put things to line up on integers. So you don't have to compute the decimals. Like what I need you to compute is the value. Like to set up the problem, I mean. Sure. Uh-huh. Yes, yes. That's the delta x that it's added. Very good. So when you partition, right, if this is your x0, then your x1 is obtained by x0 plus delta x. And then moving to x2 is going to be x1 plus delta x. So it's always to get to the next value, you always get to add delta x, because delta x is the step of moving forward through the calculation. Good. Absolutely necessary for your setup. All right, let's take a look at this together. So for our delta x, and we always start with the delta x calculation, it's 7 minus 4 divided by 4. That's 3/4. Now, whether we're going to keep it as 3/4 or we're going to put 0.75, whatever, right? What are our divisions? Now, I like to say to students, draw the partitions. It's okay, right? It's fine. Draw this and say my first number is 4. The next number is 4 3/4, right? You can put mixed fraction, you can put the decimal, or you can put the improper fraction. I really don't care which one you do. So you can say 4 3/4, right? Or you can say 19/4, or you can say 4.75. I don't care which one of the three you put, as long as you know that this division is delta x, which is 3/4 away from 4. Then you go to the next delta x, which means you are taking this and you are adding 3/4 to it. Again, I don't care which one of the four. Now, for computation purposes, right, because I don't use the calculator, I like this one, because that one gets me to compute fastest. But again, use whatever you want. So now, when I add 3, that becomes 22/4. Then I add 3 again, gives me 25/4. Then I add 3 again, which gives me 28/4. Oh wait, 28/4, that's 7. Good, landed exactly what it's supposed to at the end of the interval. So 28/4, boom, 7. Now, yes, I can simplify this to 11/2. I don't know if we're going to need it. We'll see. So now that we understand the way to break this apart, 19/4 over here, we're going to go and write our formula, right? So area will be approximated by area from the left, let's say, and that's going to be given by 3/4, which is delta x in front. And now I need to calculate f. Because I'm using left, I'll be using 1, 2, 3, 4. I'm not using 7. So that's going to be f of 4 plus f of 19/4 plus f of 22/4, which is 11/2, but whatever, plus f of 25/4. There they are. 1, 2, 3, 4. Each one gets its own delta x because it would distribute. So those are all areas of each individual rectangle. So that's 3/4 times. Now function is 3/x. So that's 3/4 plus 3/19/4 plus let's do 11/2 plus 3/25/4. And now you just simplify. Again, I'm not using calculator, so we're just doing, so 12/19 plus 6/11 plus 12/25. And you can multiply by 3/4, right? This is going to be a number. Without wasting time further, this is going to be a number. But that number, right, is going to approximate the area using the left sides. Now you can use the same one for area from the right, which would be 3/4. And now you're not using 4, you are using all others. And then we're going to use a 7, right? So we are including the point on the other side. There we go. And that's going to give us, again, the same. So we have 3/19/4 because the function is 3 over x, right? And your x is whatever is in the parenthesis. So you have to go and calculate. So 3 over 11 over 2 plus 3 over 25 over 4 plus 3 over 7. And you simplify that again. So that's going to be 12 over 19 plus 6 over 11 plus 12 over 25 plus 3 over 7. So you can turn all of this into decimals and compute, or you can find the common denominator, right, whatever it is, for 19, 25, 11, and 7. It's like the worst possible numbers to work with for this thing. But you get the idea. It's going to be equal a number, whatever it comes out to be. And now you have that your area will be in between these two numbers, the true area. Now, as I said, we are going to compute the way to compute the true area as we go through. Cool. So technically, these are your formulas to some extent. Now, we are going to make this a little bit better, but technically, these are your formulas. Now, do you actually need a formula? No, you are breaking this into rectangles, length times width, right? Just look at it and calculate and move along with your life. But in mathematics, we like notation, and then this tends to grow into a much more interesting concept, which they starting to introduce in 5.1, but then actually do work and computation in 5.2. So what I'm going to do is I'm going to just give the introduction to notation. Then we're going to take a break. When we come back, we're going to do the 5.2, where I'm going to actually do the calculations. Because they really awkwardly split this in a book, and I would really like to have all of the calculations in one spot. So I am going to talk about now about what is known as summation notation. Right, which is sigma notation. And this notation will be used a lot in Calculus 2 and the one chapter of differential equations and so on. So you are going to see this all over the place. So now let's talk about this. So first of all, summation notation, this sigma is actually the Cyrillic Greek version of letter S, and it stands for sum, addition. So it's a discrete type of notation, meaning that it operates over integers. So when I write the tablet, come on. When I write this and I say I goes from 1 to 5, that means whatever I place in a box will be written here 5 times. So now, if I have this, and I say just 6, that means add 6 5 times. So 6 when I is 1, then I becomes 2, add another 6, then I becomes 3, add another 6, I becomes 4, add another 6, and I becomes 5, add another 6. So the total is 30. So this is a counter. Now, those of you who are in programming, I just say you know what I is and what I++ does and all of that stuff. It's just a counter. This is the counter, right, that you have here. You are familiar with it with x0, x1, x2, x3. So it just gives these discrete values, the whole bundle, right, the integer value. And there is no xi where I is like 2.3. Like that, no. It's just 2 and then 3 and then 4 and then 5. So it counts over natural numbers, which are also known as counting numbers. So I say counter, and I use natural, also known as counting numbers only. So that's what the only thing you are allowed to use in that index. Now, this I can also show up inside. So let's say I starts this time, let's say it starts at 0, goes to 3, and you have I squared plus, I don't know, 10, it doesn't matter. Literally whatever. So the first time around, your I is 0. Okay, 0 squared plus 10. Plus, the next time around, I is 1. 1 squared plus 10. Plus 2 squared plus 10. Plus 3 squared plus 10. And we stop because you reached the end. It said, right, end at 3. So, what do you have? You have 10 plus 11 plus 14 plus 19. That's what you have when you compute these. And you just add them. That's 30, 40, 54. Right, so it adds to 54. So summation notation is used to compress these expressions, right, if they have some kind of a pattern that can be expressed within the counter. And literally you can have any formula. You can make up whatever you want. You just have to follow the rule that every integer between the 0 and 3, including 0 and 3, so every integer is used up and represented in this sum. So summation I, you can also start at 4 and let's say end at, I don't know, 7. So start at 4, end at 7, and have 3i minus 1 over I. This is okay. I can have a cosine of ix. It doesn't really matter, right? You can literally put anything in a parenthesis as long as it works. I mean, this would not be good if I was starting at 0 and then I put 1 over 0 and my summation explodes on the first term. So be careful about that. Anyway, going. Yes, that's nested. It's not a part of calculus courses. You are going to see it very briefly in one instance of Calc 2. It will not be used in calculations actually, but you can have nested sigmas throughout, and you're going to learn some really cool stuff. Well, in my never humble opinion, really cool stuff in chapter 11 of Calc 2. But yes, you can have a sigma that counts I from 1 to n. Within that one sigma where j counts from 1 to m of, and then some function here in terms of I and j. And that's fine. But again, none of this stuff is part of calculus or needed. There are certain things of this needed for advanced calculus, for math majors. When you transfer out, there will be advanced calculus course. You will find it there. And obviously graduate level courses are just riddled by these things. Even some undergraduate math is as well. But that's all 300-400 level courses. We are not going to see sigma within sigma in our class. All right, so what do we have here? Well, first number is 4. That's 3 times 4 minus 1 over 4. Plus, the next number after 4 is 5. 3 times 5 minus 1 over 5. Plus, 3 times 6 minus 1 over 6. Plus, the last number where we have to stop is 7. Done deal. That's it. And now you go and you compute. right? If you care about what this is, like it's 12 minus a quarter. We don't even need these parentheses. Just 12 minus a quarter plus 15 minus a fifth plus 18 minus 1/6 plus 21 minus 1 over 7. You can add all of these numbers and figure out the fractions, right? The common denominator and all of that stuff. And there you go, right? You get some number over here. So summation notation is there to kind of help us with these things. So now, if I use summation notation on my formula from before, where area was area from the left, which was delta x times f of x0 plus f of x1 plus f of x2 plus the f of xn minus 1 is the last one. You immediately see this index 0, 1, 2, 3, 4, right? So you say, so area is approximated by area on the left, which is equal to delta x times summation of f of xi, right? Because your counter I goes from I equal 0 to n minus 1. I hope you can see that now, because the first time around for this, I plug 0 there. There it is. The next time around, 0 changes into a 1. Okay, that's this term. And then changes into a 2 and 3, and the last term is the top of the series, of the summation. And you have the entire now formula compressed into this. Actually, let me write the right one as well. AR is delta x summation I goes from 1 to n f of xi. Boom. Oh, and we also have to add that delta x is equal to b minus a over n, right? Because that is the part of the formula which you have to compute on the side. So you are given f of x, like you always were, or we used root x and 3 over x, whatever. You can have your ln, you can have your trig, you can have a whole bunch of different functions. And you have the formula for delta x, and you have these compressed formulas now. Obviously, you will use it in the exploded form, right, to compute things. But it's nice to kind of, write these. Well, Thanksgiving is coming up. Write this on a napkin. Just leave it randomly around, See what people have to say, right? Because they're going to look at this and it's like, what the hell is this? And you're just thinking, yeah, those are just areas of the rectangle, like 3 times 2 is equal to 6. But they look terrifying, right? And it's just a middle school concept wrapped into this very, very classy and scary notation. It's like, really? I'm just adding areas of the rectangles. That's all I'm doing. And trying to make it look scary. So there you go. You can now go and successfully compute area under the curve, approximate area under the curve, and troll others at the same time. We're going to take a break, and we're going to use this now in 7.2 to make some really cool claims. But before that, let's breathe a little. So here comes back the epic music.